I'm back. Here we go. Got the Go 16 pulled up, full disc, natural color, Umasat, 60 images, lowest time frame. So here we got the same thing on the Go 16 weather satellite that's in geosynchronous orbit around the Earth, geostationary orbit, and a geosynchronous position at 22,236 miles above the Earth, taking shots of the, and you can see all the different weather bands, taking shots of this side of the planet. You still have that planet that is still appearing, cast a reflection upon the Earth. And it used to show up, well, you can see it's casting a reflection over here. Well, that's probably just the sun. But there you can see the light beam coming through, the light reflection. So I went ahead and pulled up the weather cam down at Antarctica to see if we could catch anything. This is the Davis Station, Antarctica, Australian Antarctic Division time-lapse SkyCam. So I pulled up the sunrise sunset times down there in Antarctica at the same spot, Davis. So from 4:21 a.m., which is sunrise, to 10:45 p.m. is sunset. So from 10:45 p.m. to around 4:21 a.m. it should be getting dark, or it should be dark. And as you can see here, got 8:45 p.m. November 3rd, Antarctica time. So we'll just play it. And so keep in mind, sunset should be around 10:45 p.m. and then the subsequent sunrise at 4:21 a.m. Watch how long it stays light. Now there's 10:45, it's past already. Still light. Basically, it never got dark. And then here's the sun coming up. So clearly, it's probably a pretty big planet that's casting a shadow or casting light onto the Earth. So here it is again, November 2nd. The day before it's too cloudy, you can't see anything. So here we go. There's the sun coming around, came up at 4:21. Supposed to set at 10:45, which, as you can see, it does down here. It sets. But it's still light. And there it is coming back up again. That was the day before. Okay, this is November 3rd. This is the one where we really could see it. So 10:45, there goes the sun. Supposed to set. As you can see, it doesn't. It's still light. There's some auroras, it looks like. And then there's the sun coming up again this morning, November 4th. So that's that. Here's the latest space weather run. These Folk radiation belts, as I pointed out yesterday, they quit recording at 8 p.m. on 11/1. That's Eastern Daylight Time. So, and as I covered yesterday in the morning video, gamma radiation starts to occur at 100,000 electron volts or 100 keV. That's when the energy is so strong that it starts stripping electrons from atoms and turn them into gamma rays. And from 3 to 10 gamma ray, 3 to 10 MeV, or 3 million to 10 million electron volts, that's when the gamma rays get really energetic and dangerous. So as you can see, as I pointed out in the video yesterday morning, that this has been occurring since at least late January when I first started making these space weather vids. I just didn't realize it. So let's turn to this here. We had some pretty high space solar wind speeds, and as I pointed out, the GOES 16, it's up here. This is the geosynchronous orbit I was mentioning, 22,236 miles. We got the GOES 14 and 13 up here, and I think the 15's up there as well, which are supplying all this data to create these international or integrated space weather analysis simulations. So all this data is coming from in here, and these are Earth radii, approximately 4,000 miles, 3,959 miles. So normally the bow shock's out here at about 10 Earth radii. So you can see it's being compressed on this, or drawn in, compressed or drawn in. I'd say it's being drawn in order to buck up to expel this energy here. As you can see, this energy's going out at 3:21:57. So let's just get it the same. So you can see it's going out. There's 11:03, 21:57. Whoops, 23:57. Okay. There's 21:53. Now you can see the magnetopause is still pulled in. Look here, this is one got a major solar wind speed when this stuff ejected. So you can see the times here. 9:38, 11:64. Best to click full screen down here so you can see all these smaller numbers. There's 15:64, 14:64. So that was basically the event there as far as solar wind speed goes. And there's another one up over 1,000, 11:75, 10:70, 10:54. I think the rest of the run's pretty clean as far as high solar wind speed. So there's 7:70. So that's at 04:00:17 minutes. So we had a period of about 3 hours or so where we had a lot of distress going on, and the solar wind speed was up. I gotta pull this up a little bit in order to drag this. So here's see that big ejection. That was at the last time the solar wind speed got pretty high. 1054 or 11 something, I think it was. So what I think's happening is these black polar cap field lines, normally they stream away from the Earth and they just direct all the solar wind pressure that's coming from the sun side, which is here, away from the planet. But whenever this energy builds behind the Earth, they have to close and garner energy from the Earth in order to expel this huge amount of energy coming in from the back side. So this is at 0009. So you can see the energy building behind the planet. That's all coming from Nemesis. (0009). Well, you can see we got energy here, but it's going out there. 0009. There's 09. See, it's leaving. Anyway, and I really did try to do some more research on this gamma stuff, but it's way above my pay grade. What I gave you yesterday, that's about the best I can do. Here's the Discover space satellite that's measuring all the solar wind coming from the sun. You can see the solar wind speed down here, kilometers per second, way down. So no way does that solar wind speed that I just showed you on ISWA correspond to anything that's coming from the sun. And as you can see, anything above 180 here, if you pull in the description box, open up that SolarHam space weather tutorial, anything above 180 on the phi angle equals a backside connection to a solar body behind the Earth. So you can see for most of the day yesterday and up until the present, the phi angles above 180. Density should be between 4 and 6 atoms per cubic centimeter. You can see that's pretty high, at least double, triple, quadruple, and even 5 times as much as it should be, which I think is coming from all this solar wind pressure from Nemesis. It's pushing everything and it's backing up out here, even as far as this Lagrange point L1, which this is where the ACE and the Discover satellites sit, according to all the solar wind data coming in from the sun. So these densities are piling up because Nemesis is back here somewhere, and it's exerting so much solar wind pressure. As you can see, I showed you the solar wind speeds recorded periodically around the Earth up above 1400 kilometers per second, that it's causing this solar wind coming from the sun to stack up. Therefore, you get more density occurring. And then the planet that passed ACE on the 16th of October, I think that's also contributing to this magnetopause being bumped around, because as you can see here, by these solar wind gradients and the field lines stacking up in front of the planet, these field lines are coming from that planet in front of the Earth. These field lines that are stacking up are coming from that planet that passed ACE on the 16th, ACE and Discover. And also, I think the field lines are making these solar wind variations rock the magnetopause from time to time. So that's about all I got, and looks like I'm running out of time. We'll show it to you here. See, there's the solar wind arrows, and you can see the direction of them. They're all pointing back toward the Earth because That's coming from Nemesis. God bless. Peace. I'm out.